Thank you so much, everyone. Today I'm going to discuss the impedance measurement and related market trends. Impedance measurement has been a standard method for evaluating component characteristics for a while. So I'm sure it's a familiar topic for many of you. But some of you are wondering why we are discussing the impedance measurement today. So there are roughly two reasons I can see. So we received a lot of questions about impedance measurements on a daily basis. So the many interests are arising, and we got a lot of questions. And also market trend. So with the rapid growth of AI data centers and EVs, the components landscape is evolving very fast. So we thought that this would be a good time to revisit the fundamentals and share practical know-how for getting measurements you can truly rely on. Okay, so let me start with today's agenda. So here is today's agenda. This session is divided into two parts. Part one is the why. So we'll look at how the rapid growth of EVs and AI data centers is changing the demands on power delivery and why that means we need to rethink how we evaluate components. Part two is the how. So we'll start with measurement fundamentals, then go through practical know-how for two measurement methods, or the balancing bridge and RFIB method. These are different solutions with different principles. So the techniques for getting accurate results are also different. So we'll cover each one separately. So first of all, let me start by introducing the market trends and how system requirements are changing along with them. So according to IEA data, looking at global new car sales by powertrain from 2000 to 2024, you can see that since around 2020, the share of electrified vehicles has been expanding rapidly. And for data center electricity consumption from 2020 to 2030, the projection is for a dramatic increase driven by AI-related workloads or servers from 2024 onward. So with the proliferation of EVs and AI data centers, four key system requirements are emerging now. So first, higher voltage. Bus voltages are rising to improve power transmission efficiency. Second, higher power delivery density. In EVs, it's about extending driving range through weight reduction. In data centers, on the other hand, it's about shrinking the physical footprint through higher integration. Third, higher efficiency. Reducing energy losses to boost EV performance and address thermal challenges in data servers. And fourth, faster power delivery. There's growing demand for power systems that can handle the rapid load transients you see in autonomous driving and AI data servers. So the expansion of EVs and AI data centers is fundamentally changing the requirements of power transmission systems. And let me next, where is it? Next, let me walk you through the changes and challenges at the power supply in the system level. Okay, there are four areas where system level change is happening right now. First, high voltage systems. Both EVs and data centers are moving from 400 volt to 800 volt architecture. that raises the bar for installation design, both basic installation performance and surge withstand. Surge is coming from actually inverter systems. Second, higher power density system. So more compact, more integrated systems mean heat concentration and also cooling become real challenges. Third, the adoption of wide bandgap devices, SiC and GaN power semiconductors. And they enable faster, more efficient switching, but introduce new issues, high frequency losses, high DVD distress, and EMC concerns. And fourth, a faster power delivery. AI computing creates low transients of hundreds of amperes within nanoseconds that demands both high-speed response and stable steady-state performance. And the requirements of power systems and the components inside them are changing dramatically. Next, I will give you an example about power transmission system in a data center power architecture. So three-phase power comes in from the grid, and it is converted to DC 400 volts or 800 volts by the AC to DC converter. Then isolated DC to DC converter steps it down to 48 volts or 54 volts. And non-isolated DC to DC converters generate the voltages each load needs. So roughly a 0.6 volt to 12 volts. So the key components here supporting this power conversion, the key components for this power conversion systems are transformers, diodes, FET, capacitors, inductors. And recently, thermistors have also been gaining a lot of attention as thermal management becomes increasingly critical. So components manufacturers are actually, launching a new thermistor products, and I got a lot of, emails, and they are promoting a lot of thermistor products. And looking at this particular DC to DC converter, which is a high-speed response converter. And they power the core of AI computing, such as CPUs and GPUs. And these converters generate 0.6 to 1.2 volts roughly, and need to handle nanosecond order low transients and output currents in the hundreds of amperes. And operating frequencies are also climbing to shrink the power supply footprint like megahertz orders. So specifically, these are, these converters are multi-phase buck converters, and the evolution coupled inductor multi-phase buck converters. Those converters of those topology are used in this high-speed response converters. And as a result, the electrical performance required from the component parts is changing. Actually, package form factors are evolving too. For example, in TLVR topology, trans-inductor voltage regulator topology. So it's now common for single inductor package to contain multiple inductors. And we were looking at the requirements of the high-speed response converters, but let's look at how the component performance requirements are changing due to this the change in high-speed response converters. So I will introduce two components requirement change. The first way is capacitive. So capacitance is increasing to minimize voltage drop during fast low transients, and the physical size is trending smaller to minimize mounting area. And the ESR is decreasing to reduce out the voltage variation caused by ripple current. On the inductor side, inductance values are trending down to support faster low transient response, and the size is also getting smaller. And the DC resistance is decreasing to reduce heat generation. So we are now in the sub 100 nanohenry and sub 1 milliohm range. So the question becomes, how do we accurately evaluate these components? Their specifications push farther into extreme territory. Let's start by looking at the gap between ideal and the real-world characteristics. So for capacitor, ideally it's just capacitance C. In reality, it also has ESR and ESL. And ideal capacitors, impedance decreases linearly as frequency goes up. But a real capacitor follows a curve like the red line here because of ESR and ESL. And for inductor, almost similar thing happening. Ideally, it's just the inductance L. In reality, it also has RDC from winding and core resistance and CP from parasitic capacitance between windings, right? So an ideal inductor's impedance increases linearly with frequency, but real inductor follows the red curve due to RDC and CP. So real components behave very differently from their ideal models, right? And these differences become more pronounced as the frequencies go up. So what does this mean for evaluation of these components? So let me summarize with first part with the reason. So the why impedance measurement matters. The market is shifting. EVs and the data centers are driving demand for high voltage, high efficiency, high density, and faster power delivery. That changing is what we need from components, right? So capacitors are getting smaller with lower ESR, and inductors are pushing into sub 100 nanohenry territory. But these components are not ideal elements we saw in the previous slide. So their real-world behavior depends on frequency, temperature, and bias conditions, and data sheets only tell you part of the story, right? So verify what's in the data sheet, measure what's not. That's the foundation for everything we'll cover in part 2. So what makes impedance measurement difficult? It comes down 3 things: how you connect, how you correct, and how you drive the signal. And the approach differs depending on whether you are using an out-balancing bridge or RFIB instruments. So Ryota-san will walk you through each of these. Ryota, over to you.
Okay, thank you, Nathan. I will share my slides, so please wait. Okay, so let's start with the basics. Before we get into specific techniques, we need to make sure we are on the same page about what impedance is and how the instrument works. This will make everything that follows much easier to understand. Oh, sorry, I will show laser pointer. Okay, so this slide is about what is impedance. The impedance is a quantity that represents how difficult it is for electric current to flow in the circuit. And in DC circuit, impedance essentially corresponds to resistance. In AC circuits, however, impedance includes not only resistance but also inductance and capacitance as contributing element. Measurement instruments such as LCR meter and impedance analyzers generate an AC signal and detect voltage and current to measure 2 parameters, Z and theta. These parameters, D and theta, are used to calculate other parameters such as resistance, capacitance, and inductance. Now, to measure impedance, we offer the following product lineup. There are 2 main measurement methods. One is the out-balancing bridge method, which covers a wide frequency range, and the other is the RFIB method, which is specialized for high frequency measurement. Since each method has different characteristics, I will explain them one by one. Okay, first let's look at the autobalancing bridge method. This method is used in our IM35 series as well as C meters such as 3504 and 3506. Sorry, I will go back to the slide. Okay, the main advantages of this method is its wide frequency range and wide impedance measurement range. On the other hand, it cannot cover very high frequencies. Among our instruments using this method, the IM3536 supports the highest frequency up to 8 MHz. So now let me briefly explain the terminals. It uses 4 terminals, HC, HP, LC, LP. And H and L stand for high and low, and C is for current, and P is for voltage. Okay, now let's talk about connection method. This is where many measurement errors originate before you even press the start button. The way you connect your device under test, it's called DUT, has a direct impact on what you actually measure. Meter will give you a measurement value, but obtaining accurate result requires some know-how. One important aspect of this know-how is the wiring method. For example, when measuring a DUT with a 4-terminal meter using the autobalancing bridge method, the DUT is connected using test leads. The way these test leads are connected directly affect measurement accuracy. It is not sufficient to simply connect the leads to both terminals of the DUT. The reason is that measurement leads and fixtures themselves have plastic impedance like this. The leads wires have plastic inductance and wiring resistance. And there is also plastic capacitance between high and low terminals. In addition, contact resistance exists at the connection point to the DUT. To reduce these effects, the wiring method between the LCR meter and the DUT is very, very important. There are several wiring methods, and I will introduce them one by one. First, here is the 2-terminal connection. This method, the current and voltage paths are combined before reaching the DUT. In this configuration, plastic capacitance and inductance and wiring resistance and contact resistance beyond the junction point are all included in the measured value. Although their effect can be reduced by open short correction function, which I will explain later, some factors such as contact resistance vary with each probing and cannot be completely eliminated. Therefore, this method is suitable for measurement where the influence of plastic impedance is small. Okay, next here is a 4-terminal connection. In this method, the current and voltage terminals are connected separately to the DUT, making the measurement less affected by contact resistance. Since contact resistance is typically on the order of milliohms, the 4-terminal method is recommended compared to the 2-terminal method for low impedance measurement, where this effect becomes significant. However, in high impedance measurement, it is affected by plastic capacitance like this, just like the 2-terminal connection. To achieve accurate high impedance measurement, proper shielding is essential. For this reason, the 5-terminal connection uses coaxial cables to reduce the effects of plastic capacitance. In high impedance measurement, shielding is fundamentally important. In addition to cables, measures such as using a shielded box are also very, very important. Okay, finally, the last connection method is here, the four-terminal pair connection. For DC low resistance measurement, four-terminal connection is sufficient. However, for the AC measurement, AC low impedance measurement, the situation is different. In low impedance measurement, the signal current becomes large, while the voltage sensing signal becomes small. Okay, so as a result, the magnetic flux affects the measurement, causing inductive coupling between cables. To address this issue, the signal passing through the DUT is returned through the sealed conductor. This cancels the magnetic flux and prevent inductive coupling between cables. This method is called the four-terminal pair connection. It is particularly effective for low impedance measurement in megahertz frequency range, where inductive coupling becomes significant. In addition, twisting the high-low pair for both current and voltage lines is also effective in reducing inductive coupling. Our optional measurement leads for LCR meters basically use this four-terminal pair connection. If you make your own cables, it is effective to design them so that they can operate in the same way. In this method, each shield conductor needs to be shorted in order to return the measurement current. This connection point this connection point should be placed as close to the DUT as possible. So this makes the connection more effective. Also, as mentioned earlier, twisting the cables is effective. In addition, there are specifications for cable capacitance. So please refer to the instruction manual for each product for details. Okay, next, about compensation. Even with the right connection method, your text fixtures and cables introduce some plastic impedance. If you don't remove that, it contaminates your result, especially critical when you are measuring low impedance component like the ones we discussed in part 1. Okay, I prepared the demo video to show you the effect of plastic impedance. Please take a look. Okay, I will show you the demo video. Okay, we will use the IM3536 and test read L2000 at the measurement frequency of 5 MHz. We will measure the inductance of we measure the rated inductor. Here we compare the measured inductance value with the high and low cables placed together and then separated. Here, the left side is the crossed together and right side is separated. As you can see, the measured value changes depending on the cable configuration. You can see here. This difference is caused by changes in the plastic inductance of the cable. Okay, so in the video, you can see that the LS inductance value changes depending on the cable configuration. This is because the plastic inductance varies with the cable layout. As shown, it is not possible to completely eliminate plastic component in the cables. So for this reason, LCR meters provides open short correction function. So by measuring open admittance YO and short impedance ZGS, this function compensates for the effect of plastic impedance in the measurement path. However, there is an important point to note. As demonstrated in this video, changes in cable configuration directly leads to changes in plastic impedance. Even if correction is applied, the compensation will not work properly if the plastic component changes. Therefore, it is important to keep the cable configuration as consistent as possible between correction and measurement. The influence of plastic component becomes more significant at higher frequencies. So, the higher the frequency, the more careful you need to be about this. So, compared to using cable, fixtures that connect directly to the LCR meter have less variation in plastic component, so their use is recommended. When errors cannot be fully removed by open shot correction, load correction is also effective. Load correction uses the calibrated reference, often called golden sample, to match the measured value. For example, in custom fixtures where complex plastic impedance cannot be eliminated by open shot correction alone, load correction is effective. Okay, now let's talk about the signal level during measurement. This is the topic that often surprises engineers. You measure the same component on two different instruments and get the different values. That is not malfunction. It's physics. Let me explain why. Okay, for example, suppose you want to measure the capacitor or an inductor and check whether the result matches the datasheet specification. In this case, the measured value can vary depending on the signal level and may not match the expected value. Okay, for example, some MLCCs have voltage dependence, meaning that the capacitance changes depending on the signal level. Please take a look at the following demonstration video. Okay, here we will measure the two types of MLCCs using the IM3536 and fixture, the 9677. First, we measure the class 2 MLCC. So I set the MLCC here. Then the signal level is gradually increased starting from 0.1 volts. On the screen, the third parameter from the top, CP, represents the measured capacitance. You can see that the value changes as the signal level increases. This is due to the dielectric material, which causes voltage dependence in the MLCC. You can see the capacitance value changes as the signal level increases, like this. Okay, next we measure the class 1 MLCC. Okay, I change the DUT and set the class 1 MLCC. Then in the same way, the signal level is gradually increased starting from 0.1 volts. As you can see here, the dielectric material used in this MLCC has very little voltage dependence. Therefore, the CP value does not change significantly, even when the signal level is varied. You can see the CP value is not so changed, like this. It's almost same. Okay, next let's look at inductors. Due to magnetic saturation of the core, inductors can have current dependence. Please take a look at the following demonstration. Okay, we will measure the rated inductor using the IM3536 and fixture 9262. Okay, I set the rated inductor like this. Then the signal level is gradually increased starting from 1 milliamps to 10 milliamps. On the screen, the third parameter from the top, LS, represents the measured inductance. You can see that the value changes as the signal level increases. This is due to the magnetic saturation of the core, which causes current dependence. Okay, the air core inductors, on the other hand, have very little of this dependence. As you can see, the measured value can vary depending on the signal level. Okay, so based on the level dependence we just discussed, it is important to match the signal level when comparing measured values with datasheet specifications. However, output resistance differs between LCR meters. In such cases, even if the same open terminal voltage is set, the actual signal level applied to the DUT may differ, resulting in different measurement results. To address this, LCR meter provides the CV mode and CC mode. CV mode is CC mode. CV mode is constant voltage mode and CC mode is constant current mode. These functions monitor the signal level applied to the DUT and ensure that the specified voltage or current is applied using feedback control. As shown, measurement result can vary if the measurement conditions are not consistent, so it is important to keep the conditions the same. Okay, now let's move to the RFIB method. If you are working at higher frequencies, this is your instrument. But the measurement principle is fundamentally different from the out-balancing bridge. And so are the techniques for getting accurate result. Here, connection and calibration are inseparable. You cannot talk about one without the other. Okay, so the RFIB method is specialized for higher frequency measurement. This is the measurement method used in our IM75 series. It supports measurements up to 3 GHz. Okay, so this method is quite different from auto-balancing bridge. So in this case, the test head extending from the instrument contains the measurement circuitry. From the test head, the DUT is connected using the 50 ohm coaxial transmission line. The measurement is performed between the signal conductor and the sealed conductor, similar to the two-terminal connection method. An important point here is to maintain the 50 ohm characteristics impedance matching all the way to the DUT. For example, if a signal ground breakout cable is used pathway, reflection can occur and significantly degrading measurement accuracy. In addition, the measurement signal may not be properly delivered to the DUT. So any variation in the cable characteristics beyond the test head directly contributes to measurement error. Okay, so as mentioned earlier, the key point in RFIB is to maintain the 50 ohm impedance matching from the test head to the DUT and keeping the transmission path stable. For this reason, the using fixture designed for high frequency measurement provides the best accuracy. So if you need to extend the connection, RF cables and probes can be used. However, the cable variation affects the measurement. So cables should be kept as short and rigid as possible. Okay, I will show you a demo video. In this video, coaxial to alligator clip cable are used. As shown in this demo, splitting the signal path midway causes large variation. You can see here the measurement value change significantly like this. Okay, so like this, the splitting the signal path midway causes the large variation in transmission characteristics and strong reflection and making accurate measurement difficult. And as you can see, when the non-50 ohm branched section changes shape, the measured value fluctuates significantly. Okay, so the next, I move like this. The variation is smaller in the coaxial section, but some fluctuation still remains. For high frequency measurement, please use fixtures or RF cables. Like this, the measurement is stable using these fixtures because it's the plastic, the transmission line is stable. Okay. So next I will explain the calibration specific to the RFIB method. In the IM75 series, which support high frequency measurement, the RF measurement circuit is sensitive to ambient temperature. As a result, the measurement result can vary significantly depending on the measurement conditions and unit-to-unit difference. Therefore, the adjustment in the user's environment is essential. This is performed using open, short, and load calibration. This slide shows the basic concept of calibration. For the auto-balancing grid method, the correction is mainly used to remove the effect of plastic impedance or to align the measured value. In contrast, for the RFIB method, calibration is the process of teaching the instrument the reference values of three standards: open, short, and load. One important point is that open, short, and load calibration must all be performed at the same reference plane. So when using a fixture, the calibration should be performed according to the instruction manual for that fixture. For example, when using the high frequency probe in automated equipment, the common approach is to use a reference device such as an ISS or impedance standard substrate and perform the calibration at the probe tip. Okay, finally, I will explain the slightly more advanced point, the defined value used for calibration. For example, when measuring the calibration kit, the defined value are as shown in the figure 1 here. The open is 0 Siemens, and short is 0 ohm, and load is 50 ohm. However, accuracy is based around the calibration point. Therefore, if you are repeatedly measuring the same type of DUT on the production line, it can be effective to use a golden sample of the DUT as the load standard. Also, for low impedance measurement, the defined value for short calibration is very important. A short standard is never a perfect 0 ohm. It always has some residual impedance. If this is defined as 0 ohm, that residual impedance becomes a measurement error. In such case like this, it can be effective to enter the residual impedance of the short device as the defined value for short calibration. You can see here the residual value can be input into the defined value. Okay, so the optimum calibration method depends on the customer's application. So please contact us if you need any support. Okay, here is a summary. So Nao-san, over to you.
Thank you, Ryota-san. So let me wrap up today's presentation with a quick summary of what we covered. First, the background. why passive component evaluation matters more than ever as electric vehicles shift from 400-volt to 800-volt architectures, and as AI data centers continue to scale, the industry is being pushed toward higher voltage, higher power density, greater efficiency, and faster power transmission. So in this environment, accurately characterizing capacitors and the inductors is just nice to have. It directly impacts the quality of your design. So second part, we talked about the three keys to getting measurement data you can actually use, choosing the right wiring method, eliminating parasitic impedance, and properly managing your signal levels. And if there's one takeaway I'd like you to leave with today is this one. So we need to move from just getting a reading to getting it right. It's not enough that your instrument returns a number. The question is whether the number truly reflects the component's behavior in your actual application. That shift in mindset is what separates good designs from great ones. Thank you all for your attention. So next we are moving to Q&A session. Oliver, over to you.
Of course, I have to turn on my microphone. Hello. All right. Thank you very much. That was a lot of information that we got from you. Thanks for that. I have already some questions here, but for everybody else, I would like to encourage you to please put in your questions. You please ask us anything that came to mind. If there's anything you want to recap, anything you would like to know on top of what you heard about this topic, please put on the questions in the Q&A function. I hope you have found it yet in your control panels. So we can answer the questions to you. I will start with one which seems a very hands-on question. I think so. Why can impedance measurement results sometimes be negative?
I will answer the question. There are several possible reasons for this, but the one common case is likely the improper calibration. For example, when measuring ESR, the over-calibration can occur due to differences in contact resistance between calibration and measurement. In such cases, I recommend using four-terminal connection where contact resistance can be neglected. Okay, that's the answer.
Okay, thank you, Ryota, for that. One is a bit more complex. So when measuring with bias current or voltage applied, it can be difficult to reproduce conditions close to actual operation due to limited equipment, equipment limitations. If this cannot be achieved with an LCR meter or impedance analyzer, how should the measurement be performed? What other methods would there be?
Yeah, that's a good question. So, I can imagine the limitations of the bias units available for LCR meters and the impedance analyzers. So, there are cases where sufficient bias voltage or current cannot be applied to the DUT. So, in such cases, a power analyzer can provide an effective alternative measurement approach, I believe. So by applying, an AC signal to the DUT from an external power source and accurately measuring the voltage, current, and the phase angle with power analyzer, then you can calculate the some power analyzer offer you calculation. So you can calculate the impedance utilizing the obtained voltage, current, and phase angle values under higher bias conditions. So actually, we are discussing that impedance component evaluation under operating conditions in the second webinar. So if you have interest, please sign up.
I was about to say while you're answering, that probably refers to the topic will be picked up in the next webinar, which we will announce later on. So please stay tuned. Okay, thanks for that. I have one more thing. What is that? What is the approximate impedance range of the device used for load correction?
Okay, I will answer that. Load impedance should be as close as possible to that of the DUT. So this is because as I mentioned earlier, it's because the accuracy is highest near the calibration point. Okay, that's the answer.
Okay, understood. I have one more question coming in right now. So sometimes we had problems with very specific application because for powder, for example, we see fixture into the data sheet, but they are not usable in Europe because they are not CE marked. Do you have any suggestion for probing when customers are not testing just components, but other DUTs, for example, end of waste elements, powders, or something like that?
Powder measurement. We have the powder impedance measurement system, but it's no CE marking.
Probably, but
Powder
I
impedance
believe,
measurement, you talk about the SA2634, I believe.
yeah, I
Yes,
believe
yes. No,
so.
we have this, of course. We have this also in Europe for the battery powder measurement. Yeah.
Okay. That means our solution covers the CE marking. So probably that would be a solution you can try for evaluating powder. Like the solution is more focused on battery materials. So, solid battery use that doesn't use the solvent for creating anode or cathode materials. And that system allows you to evaluate the impedance measurement for the powder, the kind of powder. So chemical components.
Okay. Yeah. Thank you. So there is it's a measurement system actually, including the hardware and also the software for the measurement analysis.
Right.
It's called the SA2634. We sell it here as a measurement as a whole complete system, and it's also available in Europe. But as now San already mentioned, it is really specified for powder measurement for the battery, battery manufacturing or battery, assembly, right? So it's very specified for that area. Any other questions at the moment? We have none coming in, but we can wait a few more seconds. So if there's others coming up, otherwise, I have questions for you actually. We do have a little poll. So if you have questions, meanwhile, for the topic, we wait a bit. We have a poll for you. We would like to get a little bit of feedback on the topic that we shared with you today on like what would you like to learn about on top? What else is there that you would like to know about? Maybe you didn't put it into a question, but there's still something you want to know. So please, very quickly, if you could do us a big favor, just going through these, only 3 questions. They're very short, just clicking, no writing involved. Okay. Okay. So technical topics. Yes, we give it a few minutes. Please just click on the answers. That would help us a lot. And also, in return, we can come up with topics that you are actually asking for and looking for. So it will be a mutual benefit, we suppose, at the end. Okay. which topics you would like to learn more about. All right. Okay, thank you very much for answering. So we have, meanwhile, also another question coming in. Why is RFIV measurement not efficient in lower frequencies measurement?
Basically, okay, I will answer. Basically, if we compare the auto-balancing bridge method and RFIB method, basically the auto-balancing bridge method has high accuracy. Then that's why if we can measure using auto-balancing bridge method, I recommend using this. So but in high frequency range, the auto balancing bridge method cannot be used. That's why that is the differences between these methods.
I see. Okay. Thank you, Ryota-san. Thank you for that. Okay. Thanks also for your answers. So I see that there are quite a lot of participants who would like to know more about impedance measurement in mounted or in-circuit conditions, and also temperature and environmental effects on impedance, as well as measurement techniques for specific components, MLCC. So by component, I think, what is the differences for each component measurement area? Thank you very much for participating in that little poll. I don't see any questions coming up so at the moment, but if there's any other questions, if you recap what we have been going through, if you maybe we can end the poll also, that'd be done. So if you want to know, like commercially, if you want to get an offer like that, or you have technical queries in the beginning, like how to use which instrument to select, what is the best fixture, also what we need, what is the best solution for our measurement needs, please contact us. We have here two contact addresses at HIOKI Europe, but also our engineers or experts that joined us today from Japan, Ryota-san and Nao-san, will be able to answer the questions. Yeah, please don't shy back to contacting us. Okay. So with that, I'd like to have to thank very much Ryota-san and Nao-san, and also announce what we already mentioned before. There will be another webinar for this topic. It's called Beyond LCR Measurements. What Nao-san already mentioned in the answer to that question that we had previously is power loss measurement with a power analyzer. So this is like what to validate passive components with this instrument. So there are other methods that can help you in this area. And we will have this webinar going on June 30th. So at the end of the month, in about 3 weeks. If you are interested in that, you can register already right now through that QR code. Do that right now from the screen or when we share the materials with you. Otherwise, we share registration links in the following weeks and you can register. So we would be very happy to see you again in the next webinar as well. For that, Nao-san, Ryota-san, thank you very much for sharing.
Thank you so much.
Thank you so much.
All the way to Japan, my greetings go out. And also thank you very much, everybody else, for participating, for your interest in HIOKI and in passive component testing. If there's any other materials, we're waiting for you to contact us. Have a nice day. Thanks for joining and see you next time.